Hey guys, today we are going to review symmetry within functions as well as transformations of functions and inverse of functions. So we'll start with symmetry. First, determine whether the graph of a function is going to be symmetric with respect to the origin. The test for that is we have to check f of the opposite of x and then compare that to the opposite of f of x. F of the opposite of x means we need to take each x and give it an opposite value. So 5 times negative x to the 7th plus 6 times negative x. When we raise something to an odd power, there's always a negative left over. So this section right here is going to remain negative. Negative 5x to the 7th. And this also has an odd power. It's the first power. So that negative will remain. So it's going to become minus 6x. So there's our simplified form of f of negative x. The opposite of f of x, we have to distribute a negative on this original function. So when we distribute that negative, we get negative 5x to the 7th minus 6x. And this is the same as this. So yes, this does have symmetry with respect to the origin. Which means, by the way, that that is called an odd function. Number 2, we start with h of the opposite of x. So that's 3 over negative x minus 3. It can be written the same without the parentheses. So that's h of the opposite of x. We compare that to the opposite of h of x. When we multiply a fraction by a negative, it doesn't matter if we leave that negative in front or if we put it in the numerator or in the denominator. If I put it in the denominator, though, it applies to the entire denominator. This one, I put the negative in the denominator, so I'll do the same here. But because it applies to the whole denominator, it changes the sign on the x and the 3, and it becomes negative x plus 3. These are not the same. So this does not have symmetry with respect to the origin, so it is not an odd function. Number 3, we're checking some more types of symmetry. We're going to decide if this function has symmetry with respect to the x-axis. If there is symmetry with respect to the x-axis, then every y value that exists on the graph, its opposite y value will also exist. So we check it by plugging in the opposite of y. And we see if we can algebraically make it match the original function. Negative y squared is exactly the same thing as y squared. The left side matches the original. This right side matches the original. There is symmetry with respect to the x-axis. The next symmetry we're going to check is the y-axis. If there is symmetry about the y-axis, then for every x value, its opposite will also exist on this graph. So we check the opposite of x. Y squared equals 7 times negative x minus 3. Now this is the first power. An odd power does not cancel out a negative. The left side matches the original, but the right side does not. There is no symmetry with respect to the y-axis. For y equals x, if there's symmetry there, then for every point xy, the point yx will also exist on the graph. So that means we can exchange our x's for y's and our y's for x's. So we start with x squared equals 7y minus 3. And if that symmetry is there, then I will be able to algebraically make both sides match the original. So I'm going to make the left side match the original. I'm going to turn the left side into y squared. And when I do that, I'll check and see what the right side looks like. So to get y by itself, I'm trying to aim for y squared. So I'm going to get y by itself. I'm going to add that 3. X squared plus 3 equals 7y. And then I'm going to divide by 7. So x squared plus 3 divided by 7 equals y. I have a y here. I'm still trying to get y squared. So I'm just going to square both sides. So x squared plus 3, quantity squared, over 49 equals y squared. I've gotten one side to be exactly the same as one side of the original, but the other side is not even close. There is no symmetry about y equals x. And the last symmetry we're going to check for is y equals negative x. If there's symmetry there, then for every point x, y, the point negative y, negative x will also exist. So I'm going to exchange my y for a negative x and my x for a negative y. I'm going to go ahead and add that 3 over, but when I do that, I'm going to simplify this also. Negative x squared is the same as positive x squared. I'm going to add that 3. And this is an odd power. That negative is not going to go away, so this side is left with a negative 7y. So I'll divide both sides by negative 7. X squared plus 3 over negative 7 equals y. Then I'm going to square both sides. So now I've got my y squared that I was looking for to match this. So I get x squared plus 3, quantity squared, over 49 equals y squared. One side matches the original, the other side does not match the original. There is no symmetry about y equals negative x. Next, we'll move on to symmetry within functions. F of x equals 1 over x. We think back to some rules of exponents. If I want to move this x into the numerator, it becomes x to the negative 1 power. It was x to the first power. When I switch things between numerator and denominator, their powers will change signs. So when we look at this first set of transformations, that right there is the function. 1 over x is the same as x to the negative 1. So that's not a transformation, that's just a different way of writing the original function. So we should not think of that negative 1 as an inverse of the original function. Outside the function, we're multiplying by 1/2. When we multiply outside of a function, that is a vertical dilation. And it is by that number, 1/2. And then when we add 3 outside of a function, that function shifts up 3 units. So that means all the y values for this function get cut in half, and then it shifts up 3. In the second set of transformations, the function is this negative 1 power. There's a plus 2 inside that function, which means this function is shifting left 3 units. Then when we multiply outside the function by a negative, that's a vertical reflection. So that means this function is going to flip over the x-axis. And the last set of transformations for number 4, the function is right here. That -1 is not inside the function, even though it's inside the absolute value, it's not inside the function. Then there's absolute value, so there's the -1 outside the function, there's absolute values outside the function. We're going to do that minus 1 first because it's inside the absolute value. Minus 1 outside of function means it shifts down 1. And then taking the absolute value means all the negative y values will flip over the x-axis. So this original function would look approximately like this. When I shift that function down 1 unit, now it looks like this. And then when I do the absolute value, anything that's below the x-axis is going to have to flip over the x-axis. So it's going to look about like this on the right side, and all this on the left side is going to flip over the x-axis. So it's going to look about like that. Number 5 is an absolute value function. So its original graph will look about like that. In the first set of transformations, we're multiplying by 2 inside the function. When you multiply inside of a function, that is a horizontal dilation by the reciprocal, so that's going to be by 1/2. So all the x values will be cut in half. And then we add 1 outside the function, so it will shift up 1. Next, we have a minus 2 inside the function. This is going to move 2 units to the right, and then it will shift up 4. And the last set of transformations, everything is inside the function. So first, there's going to be a horizontal dilation by the reciprocal, so by 1/3. And that plus 6 means it's going to move left, and it's going to be 6/3. We won't keep it as 6/3. 6 divided by 3 is 2. This function shifts 2 units to the left. Identify the parent function. This is a square function, so the parent function is f of x equals x squared. 0 squared, 1 and -1 squared, 2 and -2 squared, 3 and -3 squared are part of this parent function. I'm going to dot that in because it's not actually part of my answer. My answer will be first, the identification of the parent function, and second, the graph of the transformation. The transformation that takes place here is a minus 5 inside the function, which means it's going to move 5 units to the right. So all of these points will shift 5 units to the right, where they originally were. And I'll make this one solid, because that is my final answer for the graphing part. F of x equals x minus 5. The parent function is f of x equals x. So that's the line y equals x. I should be dotting that in because it's not actually my answer. And the transformation that takes place is outside the function, so that will move down 5. So I'm going to shift that graph. I'll use the y-intercept down 5 units. It's got a slope of 1. So that's my final graph for number 7. Number 8 and 9, graph the inverse. To graph an inverse, first thing I'm going to do is look for any integer coordinates. And what I'm going going to do with those is take their x and y values and reverse them. So negative 7, 1 is going to be graphed as 1, negative 7. Negative 4, 2 will be 2, negative 4. Negative 1, 3 will be 3, negative 1. 2, 4 will be 4, 2. And 4, 7 will be 7, 4. So that is the graph of the inverse. Now, if I dot in y equals x, I should be able to see that a function and its inverse are a reflection of each other over the line y equals x. It gets a little bit more tricky when there's a curve involved. First, I'm still going to pick the integer coordinates. But I'm going to pick a couple other coordinates along the way that I will approximate so I can get the right curve. I'll approximate that one and maybe this one right here. And I'll do this one. So negative 6, 1 is 1, negative 6. Negative 5, maybe a little bit over a half. 3 becomes 3, negative 5, and a little more than a half. Negative 5 and about 4 and a half, 4 and a half, negative 5. Negative 4, 5, 5, negative 4. Negative 2, 4, 4, negative 2. 0, 3 and maybe 3/4. 3 3/4, 0. 2, 4, 4, 2. That should appear to be a reflection over the line y equals x. Now we're going to find an inverse of a function algebraically. F of x equals, same thing as y equals. So I'll switch my x and y. So x equals the cube root of y plus 3 minus 6. Now I need to solve for y. So I'll add 6 to both sides. To get rid of that cube root, I'm going to cube both sides. So I have x plus 6 cubed equals y plus 3. Then I will subtract 3. X plus 6 cubed minus 3 equals y. So that's my inverse. In function notation, that would be f inverse of x equals x plus 6 quantity cubed minus 3. Number 11, my y is going to become an x. All of my x's will become y. So I can, I didn't change all my x's to y's like I said I would. I can actually cancel a y out of all three terms here. So I'm going to do that. So I get x equals 3 over y minus 2. If I think of this x as an x over 1, I can always switch diagonally. That's a property of proportions that I can exchange diagonally. So I'll have y minus 2 equals 3 over x. And now to get y by itself, I need to add 2. Y equals 3 over x plus 2. That is my inverse. In function notation, f inverse of x is 3 over x plus 2. They both mean the same thing. The second one here is function notation. An even function is symmetric about the y-axis. An odd function is symmetric about the origin. And a function and its inverse are symmetric about y equals x. The next video I'll post will be the same review but a form B. So same concepts, different numbers.